Hello, students, and welcome to our continuing lesson on trigonometric ratios. And we approach sort of the highlight of trigonometry, or at least one of the many terrific highlights, which is the unit circle. Now, the unit circle is defined as follows. It's a circle with a radius of 1, a center at the origin, and these angles here are pi over 6, pi over 4, and pi over 3. So I just label this right here, pi over 6, pi over 4, pi over 3. And all the other angles in the first, all the other angles in the unit circle are reflection of angles in the first quadrants. For example, this angle right here is a reflection of this angle right here in the first quadrant all the way around. And our goal here is to fill in all of the points here on the unit circle. What are the coordinates of these points? Okay. And so it's probably best if we just start out with the ones that are on the axes themselves, because those are probably the quickest, fastest way to get these. The radius is 1, so this is 1, 0. That's already given to us. Up here, this is 0, 1. On the left, this is negative 1, 0. And at the bottom, this is 0, negative 1. And now we are given the task of trying to figure out the rest of this circle. And so I'm going to start at this first point right here with a rotation of pi over 6. I'm also going to write in, for convenience sake, the angle measure in degrees. So pi over 6 is 30 degrees. And if I want to find this point, well, if I want to find x and y, what I really need to do is somehow produce a right triangle. And this length here is going to be x, and this length here is going to be y. So I can figure out what these lengths are. I can fill in those points. So I'm going to take my unit circle and pull it to the side and use my whiteboard here to help me answer some of these questions. So I'm going to just draw this part of it. I know from what's given to me that the radius is 1. This length here is something x. This length here is y. And this angle is 30 degrees. Okay. So what I have here is really a 30, 60, 90 triangle. And in a 30, 60, 90 triangle, I'm going to call this thing here R. Okay, just because the radius is 1. So I know that R is equal to 2x, and I know that y, I'm sorry, this is not correct. I know that R is equal to 2y, because that's the shorter of the two legs, and that x is equal to y root 3. Okay, this is from the 30, 60, 90 theorem. Now I need to find the values for x and y. I already know r. Well, knowing r, I can take this equation and I can say, look, r is equal to 1. So 1 is equal to 2y, divide both sides by 2. That means y is equal to 1/2. Since y is equal to 1/2, I can use that fact to help me solve for x. Whoops, let me use a slightly different color here. I can use this fact to help me solve for x. Well, x is equal to y square root of 3, but y is equal to 1/2. So I substitute that in there. We can simplify, and we know that x then is square root of 3 over 2. Y, the variable, is 1/2. So I can take out my unit circle now and fill in that section. I know that x for this is square root of 3 over 2, and y is equal to 1/2. Then, next point. This time it's pi over 4, that's the angle rotation, and this is really 45 degrees. And I can use my triangle, the same idea before, and draw out a triangle. This right here, this length here is r, which is equal to 1. This is 45. This then has to also be 45 degrees. Boy, that's small and sloppy. 45 degrees. This is x, this is y. Now, from the 45, 45, 90 theorem, we know that r is equal to root 2 times one of the sides, x, and r is also equal to root 2 times y, and we can also see that these two sides here are the same, so we can say x equals y. Well, this one isn't too difficult to do. I can use this fact that r is equal to 1, and this fact here, just substitute 1 in for r. Solving for x, I have 1 over root 2 equals x. Rationalize the denominator. Root 2 over 2 equals x, which is also equal to y. So taking my unit circle back, the second point that I have here has to be root 2 over 2, root 2 over 2. One more triangle, this time it is pi over 3 radian, so this is 60 degrees. And I'm going to go back to my picture, draw this out. This time I have an angle that is 60 degrees. This is x, this is y, this is r, and we know that r is equal to 2. Well, this angle right here has to also be 30 degrees because it's a 30-60. So we can use the 30-60-90 theorem again. This time it's just that the sides are named differently than they were before. So we know that r now is equal to 2x because x is now the shorter side. And we know that y has to also be equal to x square root of 3. Using what we know, we can say 1 is equal to 2x, therefore 1/2 is equal to x. The other fact that we can figure out is we know that y is equal to x root 3, so using this here, y equals x root 3, but x is equal to 1/2, so this is 1/2 root 3, which means y is equal to root 3 over 2. And now I can fill in my circle. X is equal to 1/2 and y is equal to root 3 over 2. And really, once you have the first 3 points here in the first quadrant figured out, you can pretty much do the reflection and figure out the rest of them. So I take this point here, reflect it over the y-axis. So the x values is going to be negative. So this is negative 1/2 root 3 over 2. Take that same point and reflect it down here. Whoops, reflect it down here. I'm sorry, down here. This point here is going to be negative 1/2 negative root 3 over 2. That same point is this one right here, just reflected, so this is positive 1/2 negative root 3 over 2. Now let's do the one for 45 degrees. That's reflected across here. So this is negative root 2 over 2, root 2 over 2. Reflected downwards, down here, and this is negative root 2 over 2, negative root 2 over 2. Okay. Reflected across, this one is positive root 2 over 2, negative root 2 over 2. And then this point here, flipped this way, this is negative root 3 over 2, positive 1/2. Flip it downwards, negative root 3 over 2, and negative 1/2. And then flip it to the last side, this is positive root 3 over 2, and negative 1/2. And so there you have it, all 16 points on the unit circle filled out. And now we have this business of figuring out what all these angles are. Well, this one right here is 60. This is 90, so you're adding another 60 to it. So this is going to give you 120 degrees. Okay, I'm sorry, I said that a little clumsily. From 60 to 90 is 30, so from 90 over to this side is also 30, so it's 120 degrees. From 45 over here is 45 degrees, so from 90 to this length right here has to be another 45, so it's 135 degrees. And actually at this point I should really just label the quadrantal angles. This is 0 degrees. Up here is 90 degrees. Over here is 180 degrees. And down here is 270 degrees. And if I want to, I can also say that this is 360 degrees. Okay. So now back to our picture. I can also look at this as from 0 to this point here is 30. So I'm adding on 30. To get to this point, it's 180. Going backwards 30, so now it's 150 degrees only. From this point is really going from 180 downwards another 30 degrees, so this is 210. And then going from 180 to this point is like going from 0 to 45, in order to adding on 45, so this is 225 degrees. Getting to this point, we can go to 270 and sort of backtrack about 30 degrees. So this is 240 degrees. Getting to this point down here, it's getting to 270 and going another 30. So this is 300 degrees. Getting to this point, it's 270, going forward another 45. So that's 315 degrees. And finally getting to this point is going to 360 and backtracking 30 degrees. So this is 330 degrees. Another way that I can check is to make sure that all of the increments are the same. So this is 30 to 45, that's 15 degrees right here. Another 15 right here. So look at all of these. 120 to 135, that's 15. 135 to 150, that's 15. I can check it here, check it here, check it at all of these points around the circle. Now, one last final task before we proceed, or before we complete our circle fully complete our circle, is to figure out what the radian measures are. We know this is pi over 6, pi over 4, pi over 3. So the way I like to look at this problem is, I mean, we can certainly convert all these numbers to radian using a calculator, using the conversion, but it might help you more to think about these in terms of increments or in terms of fractions of pi. For example, if you wanted to get this to this 30-degree angle here, you go from 0 up to here, and that's an increment of pi over 6. These quadrantal angles are, let's do that first. I keep forgetting those. This is pi over 2. This is pi. This is 3 pi over 2. And then this is 2 pi. Now, back to this. From this point here to this point here is pi over 6. So if I want to figure out this point here, I go to 180, or pi, and backtrack pi over 6. Pi is really 6 pi over 6. Okay? Pi is really 6 pi over 6, and I can backtrack a little bit. I can go from 6 pi over 6 minus pi over 6, 6 pi over 6 minus pi over 6, and that's how I'm going to get to this point here. Well, that's just 5 pi over 6. So this is now 5 pi over 6. And let's keep going. If I wanted to get to this point here, I start at 6 pi over 6, and I increment another pi over 6. So 6 pi over 6 plus pi over 6 is 7 pi over 6. Okay. If I wanted to get to this point down here, well, what I really needed to do, this point right here, what I really need to do is to go to 2 pi and then backtrack pi over 6. So 2 pi is really 12 pi over 6. So this point here is 12 pi over 6 minus pi over 6. That's 11 pi over 6. And now I can do that with the other increments as well. That was the increments of in terms of 1/6 of pi. Now let's do 1/4 of pi. From pi back to this point here is going to be pi over 4. So pi minus pi over 4 is 3 pi over 4. Getting to this point down here, pi increasing by pi over 4. So that's 5 pi over 4. Getting to this point right here is from 2 pi, going back and subtracting a pi over 4. So that's 7 pi over 4. And that gives me all of my fourths, and let's do all of the thirds. Going to this point here is pi over 3. So if I want to get to this point, it's pi minus pi over 3. So I can write this here. Pi minus pi over 3, which is 2 pi over 3. Okay. Getting to this point down here, it's pi plus pi over 3. So this is pi plus pi over 3, and that's going to give you 4 pi over 3. And our last point right here, that's 2 pi minus pi over 3. So 2 pi minus pi over 3, and that is going to give me 2 pi is really 6 pi over 3 minus pi over 3, so that's 5 pi over 3. Now my picture is a little bit cluttered here because of a little bit of the calculations I did. I highly recommend that you draw your own unit circle, see if you can draw in all of the points, see if you can fill in every single one of the points. How do we use our unit circle? That's a really important thing. We kind of made this weird circle, and I really haven't explained why it's useful yet. So let me give you some quick examples right now of why the circle is helpful. So let's say I had a problem and I need to find the sine of 7 pi over 4. So what I can do is draw my circle, and this is the unit circle. To figure out that 7 pi over 4 is right here, 7 pi over 4 leads you to this point right here, 7 pi over 4. That's how much it's been rotated. And if I wanted to find the sine of this, well, the sine of this is just y over r. But we know that in the unit circle, r is always 1. So this is always 1. The coordinate of this point is square root of 2 over 2, negative square root of 2 over 2. So to get y over r, well, it's negative square root of 2 over 2 divided by 1, which is just negative square root of 2 over 2. So you can kind of see here, one of the useful things about the unit circle is that we don't have to do so many division problems anymore, because we've set the radius or the hypotenuse analogously to 1. So if you wanted to find a ratio, you just find that coordinate. Okay, so let's do another one. What if I wanted to find the cosine of 7 pi over 6? So you can look on your unit circle, know that going all the way to here, this is pi, so 7 pi over the 6 is approximately here. And the coordinate of this point is negative root 3 over 2 and 1/2, and negative 1/2, I should say. Well, cosine is just x over r, but we know that r is always 1. R is always 1. So x is just negative root 3 over 2 divided by 1. Well, that's just the x coordinate. So negative root 3 over 2 is our final answer for that problem. So with this in mind, we can find the cosine and the sine very, very quickly if we know the unit circle, because the cosine is just the x values of each one of these points, and the sine is just the y values of each one of these points. Okay? So that is very, very significant and important, and I'm just going to write it down here on my unit circle, down here at the bottom. Cosine of theta is just equal to the x values of a point, of the point, I should say, of the point on the unit circle after rotating theta degrees or radian. Let me zoom in on that. Okay. The cosine of theta is just the x value. So if you wanted to find the cosine of 11 pi over 6, well, you rotate all the way down here to 11 pi over 6, and the x value of that will tell you right away that the cosine of 11 pi over 6 is square root of 3 over 2. Sine of theta is the y value of the point on the unit circle after rotating theta. Theta, and this could be, degrees or radian. Most likely going to be a radian with all the work that we're doing. So if you wanted to find like the sine of 4 pi over 3, just look at the y value. That's going to be negative square root of 3 over 2. Okay. So I've created some problems here for you to try on your own. Try to do them without a calculator. Try without the unit circle at first. See if you can draw your own circle and figure out where it is. And if you have a hard time, go back and reference your unit circle. Okay, and this is one of the key fundamental concepts in trigonometry and in pre-calculus. It's something that you should internalize, either by memorizing some of these, or by repeating and getting help until you fully understand the concepts, and really some combination of both is best for you. So make sure you put in the time that you need to put in for this, because it is critical to your progress and your success in any sort of work that involves trigonometry. Okay, thank you for watching. Have a wonderful night, have a wonderful evening, or wherever it is and whenever it is that you are today.